So I believe we stopped here last class. Um, all right, so we looked at, we introduced the topic of circuit analysis. We looked at what circuit analysis is, basically determining the unknown voltages and currents in the circuit, right? So when you first begin analysis, okay, so when we first begin analysis, we have no idea what direction the currents are flowing or what the polarity of the voltage is, right? And so what we do is we typically just begin assigning values and direction, not values, sorry, assigning directions to the currents and the polarity to the voltages randomly, completely random. Okay. Now, the assumptions that we make about this, the current directions and the voltage polarities, those assumptions are based on certain logic, and we'll talk more about those, later on in this chapter and the next. But for now, just see that in this circuit A, B, C, D, E, there are some components. Here we have 1, 2, 3, 4, 5. We have absolutely no idea what the components are, nor do we care. When we first begin analysis, we just randomly assign the direction. So I1 is actually going up, I2 is going down, I3 is also going down. And when I say up and down, I'm just referencing the circuit diagram. Okay, I'm not talking about like a real life circuit in front of us, not in the physical world. So I1 is going up in the circuit, I2 and I3 are going down. If we had a circuit in front of us, I would say the current is flowing in this direction or this direction in the component, right? So there is no up and down in there. It's just a visual representation. That's all. And same thing with the voltage. Voltage always has polarity, right? Now, current always flows through. Remember, current is like the fluid flow, right? Fluid always moves through a pipe. So current always flows through a conductor. Excuse me. Voltage or electrical voltage is nothing but the difference in electrical potential between any 2 points. Okay, electrical voltage is the difference in potential between any 2 points. And so if it's the difference, then it's 1 point minus the other. And so we signify that by using a sign for the voltage, like a plus and a minus sign. So when you first begin analysis, we have absolutely no idea which end of the component is plus and which end is minus. And so we do the same thing again. We just simply randomly assign a polarity to that voltage. So you can see V1, V2, V4, they're all randomly assigned. Okay, so you make certain assumptions, but those assumptions are based on logic. And as long as you're consistent within the problem, your answer at the end will always be correct. When I say consistent within the problem, I mean that if you choose a current direction I1 going up like this, you cannot change that assumption halfway through your solution. You have to stick with that assumption to the end of your problem. Okay? And that's what I mean. Yes.
So we need, I remember they were saying like the whole center of like current. So we need to assume that it's possibly always from when the current is going from higher to lower potential, or do you
It always goes from high to low, and we'll talk more about that too. Yeah, it always. But there are exceptions. Okay, if you're talking about a source, then it's different. But we'll talk about that when we get to that topic. All right. So reference directions. Um, for current and for voltage both, we have single subscript notations and a double subscript notation. Here we are talking about a double subscript notation. So if you look at this component, it's a resistor, but again, it could be any component. We don't really care. It has 2 points, A and B. If I say IAB, I mean current flowing from A to B, or current originates at point A and flows through B. If I say IBA, I'm talking about current flowing in the other direction, going from point A to point B. Sorry, point B to point A. So IBA moves in the opposite direction. Okay. IAB means it's going from A to B. IBA means it's going from B to A. Now, oftentimes it may happen that you have a single subscript, R. And R is just the notation for that component, resistor R. If we write IR, we are simply saying it's the current for component R. That's it. We are not specifying any direction for that current. We are simply saying it's IR. That's the current for the component R. What if that R was R1? Because there will be circuits which have multiple resistors, multiple components, right? Then you would have I R1. It may seem like a two subscript notation, but it's not. Okay, so that sometimes causes confusion. I just want to make sure everybody understands. So when you have something like this, it's a two subscript notation, but it does not mean that it's talking about 2 points R and 1, right? Obviously, if you go to look in a circuit, if a component is called R1, automatically our brains adjust and we automatically know that we're talking about this component R1. But when we actually write the notation, it's IR1, it's still referencing just the current for R1. And that's it. Yes. If they don't assign, you can, so if it's just a number is given, you're free to choose whatever label you want to give. Yeah. You can give A, B, C, D, E, 1, 2, 3, 4, 5, doesn't really matter. Yeah. Um, so IAB and IBA, again, the first subscript or the first point is the point of origin, the second is the point of exit. In real world, if you're performing a measurement, if you take a meter and you want to measure the current flowing from point A to point B, this means that the positive terminal of your meter is going to be at A, negative is going to be at B. Similarly, on IBA, positive is going to be at B, negative will be at A. So when you actually take a meter will have two terminals, positive and negative. And so the positive terminal of the meter will go to the first point, negative will go to the second point. Okay, so that's reference directions. All right, any questions? Same thing with voltage. Voltage, you have VAB and you have VBA. Here you have a resistor which has terminals A and B. VAB means you're measuring voltage at A, the reference is at B. So VAB means measure at A with reference to B. Remember, electrical voltage is the difference in electrical potential between any 2 points. Okay, between any 2 points. So it is 1 point minus the other. Okay, so if you say VAB, we are saying A minus B. If we say VBA, then it's B minus A. If both of them are the same exact potential, then the difference between the two is zero, right? The exact same level, then the difference in electric potential is zero. Similarly, VBA is positive at B, negative at A. And so it means you are measuring measure at B with reference to A. That's all it means. Again, it's the same thing. If you have a meter and you're trying to measure the voltage, you take the positive terminal, place it at A, negative terminal goes to B. All right, questions? Any questions at all? And similar to current, if we had this, if the component had a label like R, R1, R2, this was R1, VR1 would simply mean voltage of resistor R1. That's all. It does not mean anything else. VR1 will simply mean it's the voltage of R1. Okay. Now, one more point about this. Everyone's heard of ground, right? Ground is the electrical potential of ground is basically zero. And ground literally means the earth, the ground. If you've ever seen like an electric light pole, sometimes you might have seen a long cable running directly into the earth. And what it's doing is taking the excess or leakage current and it takes it directly into the ground. And that's what happens when electricity comes to us through the hot line and returns back to the negative. At the far end, it is going into ground. And so ground level is basically zero. So if you try to measure a voltage at a certain point and your reference is ground, then the second subscript is oftentimes omitted. And so you would only get, let's say, VA or VB. And in this case, if it's VA and the second subscript is missing, and if it is obvious that A is not a component, but A is a point in the circuit, then that VA is basically VA0. Is VA0. So you're measuring voltage at A with reference to ground. The acronym G and D is what we use for ground. Okay. All right. Let's see. All right. Any questions? Yeah.
That one in the front, the symbol is the one that has like 3 miles or more in one for like.
So you're talking, oh, not the equal to, you're talking about the actual symbol for ground? That's a good point. So ground, this is the wire coming in. It's like three horizontal lines that come to like a taper with like a triangular shape. But three lines, three lines. Oftentimes you'd also see something like this. Like a triangle. You could also see something like this. This is very rare though. Not seeing that one. This is typical and very common. Some circuits still do use these, like a small triangle. Okay, so energy and power. Okay, now we just talked about how. Well, let's go back here. Wanted to point out one more thing. IAB and IBA, the numerical value for the current is the same. The only thing that changes is the sign. So IAB is equal to minus IBA, or IBA is equal to minus IAB. Okay, they're both flowing through the same component. So it's not two separate currents, it's the exact same current. We are just referencing them separately or differently. So IAB is minus IBA, or IBA is minus IAB. Yes. So that IR1 is just referencing to the current for R1. It's not specifying direction at all. So it's not specifying direction. So yeah, it could be positive or it could be negative. Now if you say IR1 with the arrow going up, then we just know, okay, there's a current direction provided. But by itself, IR1 is not giving us the entire information. It just tells us is the current for IR for resistor R1. That's it, and nothing else. And same with the voltage. So voltage VAB is equal to minus VBA, and VBA is equal to minus VAB. And again, the numerical value does not change, right? Numerical value does not change. It's only the plus and minus signs that we are changing. That's all. Other than that, there is absolutely no difference. Okay. All right. Any questions? Did you have a question? Okay. All right. So any other questions? So when we get to power and energy, we're again talking about the same plus and minus signs, but what led me back to the current and the voltage was that in real life, we don't have a positive or a negative for the voltage or the current or the power or the energy, right? It is only for us humans so that we can write equations and we can balance them out. Okay. Mathematically, physically, law of conservation of energy always applies, right? So mathematically, when we try to solve this, in order for the law of conservation of energy to be balanced out, we always put a plus and a minus sign to certain things. The same thing with the power and energy. Okay. Now, electrical engineering, we're talking about electrical energy, but energy again. If you have a self-contained circuit, you have a source in there, or you might have multiple sources in there that's actually supplying the energy, and there'll be loads that actually receive the energy, right? So how do we distinguish between those? Well, we again use plus and minus signs. So if we have a voltage across a component, you'd have current flowing through the component, right? Anytime charge flows through a circuit, energy is transferred. The rate of transfer of energy is the power. Electrical power is given by the product of the voltage and current. So P is equal to VI. We saw that in last class. So P is equal to VI, product of the voltage and current. Now, you take a look at the polarity of the voltage, right? So in this case, polarity is given here, plus and minus. Then you take a look at the direction of the current flowing through the component. If the current is entering the positive terminal of the voltage, then the power is positive and energy is being received. If the current enters the negative terminal, then the power is negative, energy is being supplied. So on the left side of the component, you have the current entering the negative terminal. So the current enters the negative terminal, power is negative. P is equal to minus VI. The equation remains the same. The only thing is we put a minus sign in front of the equation. Okay, so P is equal to minus VI. And on the right hand side, again, you have a plus and a minus here. The current is flowing in this direction, meaning it's entering the positive terminal. So current enters the positive terminal, power is positive, P is equal to plus VI. Easy enough? So if current enters the negative terminal, power is negative, energy is being supplied. If current enters the positive terminal, power is positive, energy is being received or absorbed. Think of it in this way. Yes. Where? Oh, just this, the component. Let's call it element E. Doesn't really matter what we call it. Yes.
I remember in physics, we were talking about like the trend direction going from positive to negative. It was not usually like positive ways, like it's like negative or again getting confused on this line.
No, it doesn't really matter what it is. We don't really care what the component is. We don't really care what it's doing. But if we are given like a voltage polarity and then we are given the current direction, then we just apply these principles. Now, you will all see that when we start solving circuits, again, I keep saying, right, we make certain logical assumptions. Well, one of the assumptions is that, not assumptions, but um, uh, one of the criteria is that a current will always go from high to low, plus to minus, except for a source. So again, when we get to that topic, I will talk about those logical assumptions. But for now, this is like this is the reference configuration for the principle, meaning how do we differentiate whether a positive power and a negative power? Well, that's how we do it in electrical engineering. If the current's entering the positive terminal, we say power is positive. If current enters the negative terminal, power is negative. If you think of it in terms of money, yes, go ahead. Um, oh, you mean these? Yes, yeah. Either they are given to us in the problem or we are choosing them. Does not actually matter whether it's given to us or whether we choose. But after the assumptions are made and after we have all the information, when we apply the equations, that is what this is how we apply it. Yeah. And so if power is positive, energy is being received. If power is negative, you're supplying the energy. Okay. So if power is received, energy is positive. You're absorbing the power. And if power is negative, you're supplying the energy. You're delivering power. It's like money. If your buddy asks you for $100 and you give them $100, well, your wallet is a lot lighter, right? So you have a net negative balance, and your buddy has now $100 more, so it's a net positive for them. So based on that, we have something that we call as a passive reference configuration. Passive reference configuration. Again, all you have to do is look at the positive negative terminals of the voltage and then the direction of the current. If the current is entering the positive terminal, the equation that you will use is P is equal to plus VI. If current enters the negative terminal, the equation you would use is P is equal to minus VI. So 1, 2, 3, and 4. In circuit 1, the component has a plus and a minus, plus up top, minus down below. Current enters the positive terminal, and so power is positive. So you use P is equal to plus VI, right? P is equal to plus VI. Now, when we first do these kind of circuit setups, when you're first setting up the circuit, I suggest to students that you might want to put the plus and minus sign right next to the terminal itself. So that makes things a little bit easier. Okay, so we have a plus here, we have a minus here. Current is going in this direction, so power is positive. And this is minus here, this is plus here. You can extend the arrow here, and you can see it is still entering the positive terminal. And so power is still positive. P is equal to plus VI, right? You extend the arrow all the way, extend the arrow all the way, and you can see that it's entering the positive terminal. So if it enters the positive terminal, power is positive, you use P is equal to plus VI. Okay. On the right, we have 3 and 4. 3 and 4 is the same thing. In 3, you have negative here, positive here. You extend the arrow, and you can see it's entering the negative terminal. So power P is equal to minus VI. And here, current is entering the negative terminal. So again, P is equal to minus VI. That's the equation that you would use. And based on these, we have a few examples that we can take a look at, simple examples. So 3 elements, A, B, C. We are already given the polarity of the voltages. We are already given the current directions. All we need to do is basically apply our equations, right? So the first one, plus, minus, current's coming down this way. Power is positive. P is equal to plus VI. So P is equal to VI. 24 joules, meters. Units are standard. Doesn't matter what kind of power we're talking about. Named after James Watt. Here we have plus, we have minus. If we extend the arrow, we see it's going into the negative terminal. So power is negative. So the equation we would use is P is equal to minus VI. So this comes out to be minus 12 watts. I'll wait until everyone catches up. Third one is, well, I was just a little tricky, but it's not that tricky. You just apply the concepts and you get the answer. So you have minus here, you have plus here. You extend the arrow, you can see that it's entering the positive terminal. So the equation that we need to use is P is equal to plus VI. But if you look at the current itself, it's given to us as minus 3 amps. Minus 3 amps. Okay. You do not change anything. You simply take the values and plug it into the equation. Okay. All too often I see even students like, they would have done the hard work. They would have set up the problem correctly. They would have done everything correctly. But when they actually plug in the values, then they decide to switch something out. And that's where they make the error. So anytime you're solving problems, setting up the circuit and determining the equations, that's the majority of the work. Once you have the equations, then it's just math after that, right? So you simply plug in the values as they are. 12 minus 3, you get 36, sorry, minus 36 watts. And that's it, minus 36 watts. So you do not change anything. Easy enough, right? Questions? Any questions at all? No matter how much comfortable this is, after a while it does start to hurt. Still is much better than a lot of other earpieces. Okay. How do you say that name? Kirchhoff, Kirchhoff, Kirchhoff. So I'm from India. The way we pronounce it there is Kirchhoff. So if you ever hear me say the word Kirchhoff's laws, that's who I'm talking about. So when I first came to the US as a grad student, I was sitting in a meeting and somebody mentioned Kirchhoff. And I was like, I thought maybe they're talking about like Star Trek or something. And I was completely lost for a few minutes. It took me a while to figure out they were talking about Kirchhoff. Apparently, he was a German physicist. The actual pronunciation of this name is like Kirchhoff. Now, none of us lived in that time, so we don't know if that's true. But in modern times, whoever is this kind of name, that's how they pronounce it, Kirchhoff. Anyway, he postulated a couple of laws in theory. They are based on the law of conservation of energy. It simply means that when you sum up the currents at a junction, electrical junction, they would all add up to zero. If you add up all of the voltages around an electrical loop, they should all add up to zero. Now, assume in physics, previous physics classes, you've all done KCL, KVL, right? So you might be used to a particular method or a particular way to apply KCL and KVL. Now, KCL is rather straightforward. KVL, just there are two or three things to keep in mind. But the point is, if you are already familiar with and are comfortable with using a particular method, you are free to do so. Okay, you are not. I'm not going to try and impose my methods on you. All right, I will explain what the topic is and everything, but I'm not going to impose my method on you. So if you're already familiar with something, you're free to do that. So first, let's talk about what is a node. Okay, an electrical node is basically an electrical junction. Okay, electrical node is an electrical junction, and a node is created anytime you have two or more components come together. So anytime you have two components come together, that's a node. Okay, it's an electrical junction. It's basically like a traffic signal or a meeting of like two roads. Okay, anytime you have two components coming together, that's a node. Now in the circuit, this is kind of like bent at a right angle, right? But you could actually stretch that E out like this and make this straight. So circuit schematic is not illustrative of what exactly is happening in the physical world. So you keep that in mind. So this might not look like a junction. So if you just have a straight line between two components, you might think that this is not a junction, but that's not true. Anytime you have two components coming together, it's a junction. Okay, so KCL simply states you add up all the currents at a junction, and they should all sum up to zero. Now, one important point about current is current again is a quantity that flows, right? So it flows through. It flows through components. It flows through wires. It's like fluid. And so when we talk about junctions, obviously something is entering the junction and something is leaving the junction, right? You take any electrical node, some currents will be entering, other currents will be leaving. And so the way I write out my mathematical equations is simply this. I take the equation, all the currents that are entering the junction, I put them on the right side of the equation, and sorry, I put them on the left hand side of the equation, and all the currents that are leaving the junction, I put them on the right hand side of the equation. And that's it. That's my mathematical equation. So if I take, let's call this junction 1, 2, 3, and 4. Nodes 1, 2, 3, and 4, right? So at node 1, I can see that I have IA and IE both leaving the junction, which is physically impossible, of course. But we'll see how it works out mathematically, right? You cannot ever have two currents leaving the same junction, or well, basically for that matter, all currents entering the junction or all currents leaving. That's physically impossible. And that's where the plus and minus signs come into the picture. That's why we use the plus and minus signs, right? So mathematically, you'll see how it works out. If you have at junction 1, so nothing is entering the junction, right? So it's 0. So 0 equals IA and IE. That's it. That's my mathematical equation. Nothing is entering the junction, so it's 0. Junction is right here. I don't see any currents coming. I see IA leaving and IE leaving the junction. And so 0 equals IA plus IE, right? Now, if you want to apply it, you can also say IA is equal to minus IE or IE is equal to minus IA, but you get that from this equation anyway. So does that make sense to everyone? Right? Straightforward. And so I can write IE is minus 6 amps. And that's it. IA is given to us as 6, so IE is minus 6 amps. Now, if I take a look at node 2 up top, I can see that IA is entering the junction, IC is entering the junction, and IB is leaving. So if I apply KCL at node 2, all I need to do is, again, currents entering the junction are on the left side, so IA plus IC, and currents leaving the junction are on the right hand side, is equal to IB. So you can write IB is equal to 6. IC is given as minus 2. We do not change anything. We simply take those values and we plug it into our equation. And that's all we need to do to get the right answer. That's it. Make sense to everyone? Any questions on KVL, KCL? Yeah.
It's not, so this is the same as the Kirchhoff junction law, no? So you have like, so this is the Kirchhoff junction law, basically.
Junction law, yes, yes. Yeah.
So, like, it's not usually like the ones that go in are the positive and the ones who go out are negative, or like memory.
No, no, it's not like that. No, no. Okay, so I will leave 3 and 4 for students to practice. Okay. Again, they're easy enough. There's also another example on the next page. Sorry, not this one, parallel connections. Again, I will assign this as student practice. And then, of course, you have homework. I think there's a homework assignment that's coming up. That's like KCL and KVL. So, oh, since I'm on that topic, homework in my class is never considered to be fully assigned until and unless the topic is covered in class. Okay, so I will always push the dates back. Okay, so right now there might be some due dates that the homework is like homework 1 is due tonight, right? It's like about I think it takes about 20-30 minutes, probably not even that much to solve it. But most of what you need to solve that homework is already covered in class, so that can be considered to be done. But homework 2, I think there are a couple of things in there that I've not yet covered in class, so I will push that back. So they will not be due until and unless I cover those topics in class. Okay, so if you see the due dates on there, don't get worried. You can get started on it if you wish to, because some of it is covered, some of it's not. But until the entire topic is covered in its entirety, I will not make it due. It will be pushed back. Now KVL and KCL will cover in class, so KVL and KCL will be due at their on their times. So having said that, let's get to KVL. And so in KVL, we are basically summing up all the voltages in a loop, right? So what is an electrical loop, first of all? Right? Electrical loop is a connection of multiple electrical pathways. Basically, the way I explain it is if you pick any point in the circuit, okay? I typically pick like the bottom left corner. So if I pick the bottom left corner, how many pathways are there for me to come back to that same corner? If I start driving from that point, how can I come back to that same point? So that's one. And then there's the outer one right there. So 2 loops right there. And then I have a third one, which is basically starting from this point right below C and going all the way around this way. So there are a total of three loops in the circuit. Three loops in the circuit. Okay, three loops in the circuit. And KVL basically states that if you add up all the voltages around that electrical loop, they should all equal to zero, or they should all sum up to zero. Again, law of conservation of energy applies. Okay, so it should all equal to zero. Now, the way I do this is I always start at the bottom left corner of the circuit or the loop, and I always add up the voltages in a clockwise direction. Clockwise. Okay. You can do it counterclockwise, you will still get the exact same equation. It would not be any different. And so this is how I do it. So if we talk about loop one, I have three voltages in loop one, right? A, B, and C. A, B, and C. And so what I'm going to do is I write down VA, VB, and VC are all equal to zero. VA, VB, and VC are all equal to zero. I just need to sum it up. Now here's where it comes, the signs come into the picture, right? Voltages are never negative or positive. It's only for us humans to be able to write mathematical equations. So I start driving around starting from this point. The first polarity that I encounter, the sign of the voltage, that is what I'm going to put in the equation. So when I start from this point and go around the loop in a clockwise manner, start from this point, go in a clockwise manner, I get minus VA plus VB plus VC. And that's all I'm going to do. Minus VA plus VB plus VC, and I have my mathematical equation. And that's it, as easy as that. Does that make sense to everyone? Right? Now, again, as I said, KVL is a little more involved when you try to apply the principles. So if you have a preferred method, you're free to use that. Does not, no matter what method you choose, the equation will be the same. Okay. If you choose this method and you go counterclockwise instead of clockwise, you would still get the exact same equation. So if I start at this point and I go counterclockwise, well, I would get VC, VB, and VA equal to zero. Now my VC is minus, VB is minus, and VA is plus, right? I encounter minus, minus, and plus. Make sense? So this would be counterclockwise, counterclockwise, counterclockwise. And the exact same equation. There's no difference between these two equations, right? And that's KVL. That's KVL. So let's take a look at an example. But did that make sense? Right? So here, you have one, two, three. How many loops do you see in here? Three loops are obvious. And then fourth, one around, yes. Five, and then six. So here, so you got one, two, three, right? So that's three. The outer one is four, right? This is five, and then this is six. So any electrical pathway that allows me to come back to that same point is an electrical loop. Any closed electrical pathway is a loop. And the beauty of KVL is that it doesn't matter what loop you take, it always holds true. So you can apply it to any of these six loops, and your KVL equations will always come out to be true. So let's take a look at the first one. Actually, let's take a look at the outer loop. That has more components, right? So we have A, C, E, and F in that outer loop. So the outer loop, you have A, C, A, and F. So I'm going to write out VA, VC, VF, and VE is equal to 0. I start at the bottom left corner and I start driving around in a clockwise manner. VA is plus, VC is minus, VF is plus, and VE is minus. And so it will be plus VA minus VC plus VF and minus VE is equal to 0. And that would be my KVL equation. All right. So VA, VC, VF, and VE. Let's see, do we have enough information to solve it? Yes, we do. So we can find VF because all the other three quantities are given to us. So A, C, and E are given to us, right? A, C, and E. Simply plug it into the equation and we get VF. And that's it. So since you're already here, we may as well solve it. We have plus 10 minus 15 plus VF minus 20 is equal to 0. So VF is equal to 35 goes on the other side, 10 goes minus, so 25 volts. Somebody perform that calculation. Let me know if I'm correct or wrong. 35 plus 10, 25 goes on the other side, plus 25. Yeah, plus 25. Right? All right. Questions. Now, there are a couple more topics I need to talk about in this chapter, but we are just about out of time for today. So I will end class here today, but there will be a quiz on Monday. It's a 20-minute quiz based on the topics that we have covered so far. There are equation sheets that allow students to use during the quizzes. You can write anything that you want on there. Any kind of equations, methods, methodologies is fine. Completely solved problems or circuit diagrams are not. So pick one up on your way out. And again, as I said, you will use this sheet for the entire quarter and it's divided into quarters, front and back. So you feel free to use one quarter today for quiz one. All right, have a good weekend and I will see you next week. So solved problems or entire circuit diagrams are not allowed, but like equations, laws, anything that helps you remember some stuff is fine.
Oh, so like right now, like the method of putting positives and negatives is
That's fine. Yeah, methods, methodologies is fine.
like what would be illegal, for example, in this case?
Not really sure. Like,
Yeah, because I'm scared because if I write something illegal, that would be really